All right. Our next speaker this afternoon is Brayan Hernandez, who's joined us this summer from UCLA. Brayan's been working this summer with Rieko, and he'll tell us about their project together, identifying and characterizing properties of Lyman-Alpha blobs at redshift 4.9.
Hello, everyone. Thank you, Gwen, for the introduction. So prior to this project, I had never heard of Lyman-Alpha blobs. And throughout this summer, I realized that most people in the field don't really know what these objects are. And so to give a little background of what Lyman-Alpha blobs are, is they are these galactic scale gas structures that are very bright in Lyman-Alpha mission. And they have an extended gas structure. Oh, my bad. Oh. They have this extended gas structure beyond the host galaxies. And so this extended structure is believed to be the circumgalactic medium and parts of the intergalactic medium around these host galaxies. And for those unfamiliar with Lyman-Alpha mission, that's just the transition state from N2 to N1 in neutral hydrogen. And this emits a specific wavelength of 121.6 nanometers. And so we can use Lyman-Alpha blobs to probe circumgalactic medium and intergalactic medium. Generally, these media are too dim and diffuse to see, especially at high redshifts. But with Lyman-Alpha blobs, they're bright enough to see. And so we can use them to figure out the roles that the CGM and IGM play in galaxy evolution. However, there's one huge caveat with Lyman-Alpha blobs, and that's due to their rarity. There's only a handful of them that we have identified, and there's a lot of uncertainty of their properties and the properties of their host galaxies. The biggest mystery behind them is exactly what's powering their Lyman-Alpha mission. We're not sure if that's the same for all Lyman-Alpha blobs. It could be a degenerate process. So to tackle this uncertainty, my project this summer consists of 2 parts. The first part being a Lyman-Alpha blob catalog of 18 Lyman-Alpha blobs, and I'll go into the specifics on how I found these objects. And then once I had my catalog, I just analyzed their environments and cross-matched them with AGN sources. So the setup for my Lyman-Alpha blob catalog was data from the Subaru Hypersub Prime camera, HSC for short, and there's just an image of it right here. And I used data specific to the Cosmos field. And so I used a specific narrowband filter, NB718, and this has a narrowband peak at 718 nanometers. And so any Lyman-Alpha emission in this narrowband filter corresponds to redshift at Lyman-Alpha emission at redshift 4.9. And so to give you guys an idea of how I found these objects, the image on the right shows the spectra of 2 different types of galaxies. For the case of Lyman-Alpha blobs, it would be the red spectra, since these are Lyman-Alpha emitting galaxies. And this spectra is specific to Lyman-Alpha emission at redshift higher than 4.9. However, the general idea still remains the same across all redshifts. And so first, you want your narrowband filter to cover the emission line of Lyman-Alpha. And so this narrowband filter will not only pick Lyman-Alpha emission from Lyman-Alpha blobs, but also the continuum of their host galaxies. And so to get rid of that galaxy continuum, we can use a broadband filter at higher redshifts, at higher wavelengths, to gather the continuum of the galaxy. And because this continuum is relatively flat, we can just subtract the broadband from the narrowband. And so to give you an idea of what that looks like, here's an image in the narrowband filter, and here's an image in the broadband filter. And when you subtract these, any excess should be Lyman-Alpha emission. And so this object specifically is Z49-1, which was the only previously confirmed Lyman-Alpha blob in the Cosmos field at redshift 4.9. And so using this method, I was able to find 17 more. And here's just how they look like. And so I had a plentiful harvest this summer of Lyman-Alpha blobs. And so now that I have this catalog, I can look at their environment, specifically their density, and cross-match them to see if there are any nearby AGN sources. And so previous studies have found a strong correlation between Lyman-Alpha blobs and overdense regions. The image on the right is an overdensity map of the Cosmos field at redshift 4.9. And the darker the blue, the more dense the region is. And so as you can see, Z49-1 is in a very overdense region. And this seems to be a general trend for all the previously confirmed Lyman-Alpha blobs. There seems to be, it's thought to be believed that overdensities of the environment play a role in the Lyman-Alpha emission of these objects. And this paper specifically, Zhang et al. 2020, used Lyman-Alpha emitters to probe this overdensity, which are these dots right here. And so I did something similar with my project this summer. I used a newer catalog of Lyman-Alpha emitters that was released earlier this year in Kikuta et al. 2023 to determine the overdensity of the cosmos field. And so all the Lyman-Alpha emitters are depicted as the cyan dots, and the green corresponds to where the Lyman-Alpha blobs are. And so to calculate the overdensity, I used a circular aperture of 15 co-moving megaparsecs and determined the relative number density of Lyman-Alpha emitters in that aperture. And so the number density within the aperture is denoted as sigma LAE, and then you divide that by the average of the whole region and then subtract 1 to get an overdensity parameter known as delta LAE. And so this results in the following histogram for my Lyman-Alpha blobs. And so here are two populations. The blue is just the Lyman-Alpha blobs, and the yellow are the Lyman-Alpha emitters I used to probe the overdensity. And so the red line is the average density of the region. And as you can see, 72% of my Lyman-Alpha blobs are in overdense regions. However, this was not expected because previous studies found an exclusive relation between Lyman-Alpha blobs and overdense regions, and I found some that were underdense. For the ones that are overdense, this overdensity is still too small compared to previous studies. And so there could be two reasons why this was the case. The first reason could be that where the Lyman-Alpha blobs are more towards the edges of their density regions rather than the centers. And so when I took a circular aperture of 15 co-moving megaparsecs, it wasn't able to collect all the Lyman-Alpha emitters in the density region. And so another way to look at the density would be making a density map similar to Zhang et al. 2020. And here's kind of my preliminary result I got earlier this week. And I'll be working more with it soon. And then a second reason, let me reiterate. But if I do find that some Lyman-Alpha blobs are in lower densities, it could be that the previous studies had a bias towards Lyman-Alpha blobs in overdense regions. And another characterization of Lyman-Alpha blobs that I want to look at was specifically to their host galaxies. I wanted to see if any of them were active galactic nuclei, or AGNs for short. And for those who are not familiar with AGNs, they are when the supermassive black holes in the center of the host galaxies are accreting a lot of material, and this accretion is thought to radiate energy in the form of jets outward. And so these energetic jets can excite the gas in the circumgalactic medium, which could lead to the Lyman-Alpha emission that we see. And so for my project, I cross-matched my Lyman-Alpha blobs with two AGN catalogs. And these AGNs were found in the X-ray, radio, and infrared. And I found that 0 of my Lyman-Alpha blobs had concrete AGN sources near them of around 1 arcsecond. And although this result is underwhelming, there's several reasons as why this could be the case. The first could be that the active galactic nuclei catalogs that I used were not sufficient enough, and so maybe using other ones could detect AGN sources near my Lyman-Alpha blobs. Another reason could be that these catalogs are limited to only the X-ray, infrared, and radio, and so it could miss signatures that aren't in those parts of the spectrum. And so doing something similar to what Zhang et al. 2020 did, they used an emission line diagnostic of Z49-1. So there's a certain relation between the equivalence width of carbon-4 and the ratio of carbon-4 and helium-2 that separates AGNs from star-forming galaxies. And this dashed line denotes the boundary between the two types. And as you can see, Z49-1 is sort of at the cusp of the two regimes. And although it's on the AGN side, it's still too close to call. And so it's still possible that this could be a low metallicity star-forming galaxy. However, doing something like this for all my Lyman-Alpha blobs would be a greater insight onto whether or not these actually have AGN sources. So some spectroscopy follow-up in the future could be a step in the right direction. And then the third reason could be just that high redshift Lyman-Alpha blobs don't host AGN sources. So this image on the right is a AGN volume density versus redshift for faint galaxies. And each color just denotes a different luminosity. And as you can see, the general trend is that there's a peak at around redshift 2 to 3, and it falls off as you go off to higher redshifts. And so all the previous Lyman-Alpha blobs that have been cataloged with as AGN sources were around redshift 2 to 3. However, for my Lyman-Alpha blobs at redshift 4.9, if you continue the trend, that would be a volume AGN volume decrease, density decrease of about an order of magnitude. And so that may be why I was not able to find AGN sources in my Lyman-Alpha blobs. So that was it for my project. So just to conclude, 18 Lyman-Alpha blobs were identified in the cosmos field at redshift 4.9, 17 of which are new. 72% were in overdense regions. However, with the new density map, this is subject to change. But the 72% preliminary result was very different from previous studies. And I couldn't find any Lyman-Alpha blobs cross-matched with AGNs. So in the future, I'll just be working more with the density map that I showed. And some spectroscopic follow-up of these objects would also be a good insight. Thank you. Wow.
Oh, yeah. First of all, Brian, congratulations on your discovery of 17 new Lyman-Alpha blobs. I had two questions. Feel free to answer one or like both. The first was, are Lyman-Alpha blobs detected across like a wide redshift range? Like, are there more in the local universe, early universe? And the second one is, have you tried comparing them to maybe emission line models that maybe capture Lyman-Alpha? Just curious.
Yeah, those are two good questions. So for your first question, we have observed Lyman-Alpha blobs across different redshift ranges. It's kind of from between 2 to 7 redshift, but anything below redshift 2 we wouldn't be able to detect, because the Lyman-Alpha emission in that range, in lower than redshift 2, would be in the UV, and our atmosphere kind of obstructs UV emission. And so we're kind of constrained in a certain region, but you can find Lyman-Alpha blobs throughout around redshift 2 to 7.
I had a question about, you mentioned that you selected an aperture to find the overdensity, and I was just curious about like why that specific aperture was chosen.
Oh, that's a good question. So it's thought, so protoclusters are thought to be around 10 megaparsecs in size. And so the protocluster is just like a really dense region with like, it's kind of like a local group of galaxies. And so using a aperture of 15 co-moving megaparsecs is kind of a good size to fit a whole 10 megaparsec protocluster.
Thank you.
I guess along similar lines, so is the 17 the number expected by simulations in that kind of volume, or does this come as a surprise?
I don't think there's any expectation of how many to find within that volume. Wait, can you repeat the question? The 17 Lyman-Alpha blobs in the volume?
Yeah, I would imagine that there is some prediction of kind of how many protoclusters, given like simulations of kind of galaxy formation at different redshifts, kind of how many you would expect, but maybe it doesn't exist for this exact volume. But
yeah, I'm not entirely sure on that. I can maybe talk to my mentor and then talk to you more about it later on.
Right. We have to move on. Sorry. Thank you.